Welcome to the content material for Class 6 of Engineering Statics. You should be watching this video before your 6th class. In this lesson, we will talk about how to form vectors that move between 2 points, which are called position vectors, how to use position vectors to describe force vectors that move along a line, and the procedure for computing dot products. So far, we have defined vectors using a magnitude and an angle, and we have defined vectors using Cartesian components. However, many times in reality, we do not have this information. Instead, we have the coordinate locations of 2 points, and we know that the vector goes from one point to the next. So for example, this vector r goes from the point A to B. If we know the coordinates of points A and B, we can easily define the vector r by finding the difference between the x, y, and z coordinates at points A and B. So we can use this equation to define the position vector. So the x coordinates, or the x components of the vector r, is found by subtracting the x coordinates of point A from the x coordinates of point B, and so on. Many times, the direction of a force is specified by 2 points through which the line of force acts. For example, there may be a chain. We know that the chain has tension in it, acting along the direction of the chain. If we can find the position vector r, and we know the magnitude of the force, then we can find the force vector acting along that line. We know that the vector force F is equal to the magnitude of the force F times the unit vector of the direction vector r. In other words, the magnitude of the force F times the direction vector r divided by the magnitude of it. The last topic that we'll look at today is the dot product. Earlier in class, we used trigonometry to find the angle between 2 lines. In 2 dimensions, this is pretty easy. However, in 3 dimensions, it can be difficult to determine what the angle is between 2 lines. However, we can use something called the dot product to figure that out. The dot product is a mathematical procedure between 2 vectors. So we take the dot product of 2 vectors, and the output of that is a scalar. If we need to determine the dot product between 2 vectors, and we would read this as A dot B, we can compute it by adding up the products of the x and y components. So A dot B is equal to the sum of the product of the x components of the 2 vectors, the sum of the products of the y components, and the sum of the products of the z components. And the result of that is a scalar. It's a number, not a vector. This can be useful for us because the dot product is also equal to the magnitude of A times B times the cosine of the angle between those 2 vectors, if we call that angle theta. We also have to know that the dot product is commutative, so A dot B is equal to B dot A, and dot products can be distributed. So A dot the sum of B plus D is equal to A dot B plus A dot D. So that's how to do a dot product, but why do we need the dot product? Well, there are 2 applications. The first application is that we can use the dot product to find the angle between 2 vectors or 2 intersecting lines. If we solve this equation for theta, we can see that we can use the dot product to find the angle theta between the 2 vectors using this equation. The second application of a dot product is to determine how much of a vector is parallel to another line. For example, how much of vector A is parallel to the AA axis? We can say that the magnitude of the vector A that is parallel to the axis AA is equal to the dot product of A times the unit vector along that axis. So let's look at some examples of these ideas. Okay, in this example, we see that there is a man pulling on this cord, and we see that we don't know the angle of the cord, but we do know the location of the support, which is called point A, and we know the location of the man, which we'll call point B. So the first thing we want to do is we want to draw this out. So we can draw this with point A, point B, and we want to lay out the x, y, and z coordinates. So here is our y-axis, here is our x-axis, and here is our z-axis. And we know that this is, we're told, 8 feet over in this direction, and we're told that this is 12 feet in this direction and 6 feet in this direction, while point A is 30 feet up here. And what we're asked to find is what is that force, and that we can describe it in Cartesian units. So the first thing we want to do is we want to lay out the coordinates of point A. So we see that point A is directly above the xy axis, so there's 0, 0, and it's 30 feet up in the z direction. For point B, we see that it is 12 feet positive in the x direction, so that's 12 for the x coordinate. It's negative for the y direction, and that's 8 feet, so negative 8 feet. And in the z coordinate, it is 6 feet, we're told. So now that we have that, we're going to define our r vector, this position or directional vector. And we know that that's going from B to A, or going from A to B. So we want to subtract B minus A. And for our z coordinates, we have ZB minus ZA, and we give that our z unit vector. Now we're going to plug in the values that we have already. So 12 minus 0, I hat, plus we have negative 8 minus 0, j hat, and we have 6 minus 30, k hat, and the units for all of this, in this case, is feet. We go ahead and figure that out. We have 12 minus 8 minus 24. So this is the direction of that. The force is moving in the position direction, the position vector going from A to B. We call that R, and we see that that is the units there. Next thing we need is the magnitude of R. And we know that that's Rx squared, Ry squared, Rz squared. Go ahead and plug those values in. We find that the magnitude of R is 28 feet. So next we want to find the unit vector, because we know that F is equal to the magnitude of F times that unit vector of R, because we already know the magnitude of F. So we want to go ahead and find that unit vector, and that's going to be just equal to the directional vector divided by its magnitude. So we just plug those values in. 12 over 28, 8 over 28, and 24 over 28. So now we have the values that we need. We know that the magnitude of F, we're told, is 140 newtons, and we have our unit vector here. So 12 over 28 in the x direction, negative 8 over 28 in the y direction, and negative 24 over 28 Plug those values in, we find that Cartesian units for this force vector F, 60 positive in the x direction, 40 negative in the y direction, and 120 negative in the z direction. And the units for that is newtons. Don't forget units, and that's our answer. So in this next example, we're going to again find some directional vectors, but this time we'll apply also the dot product. So if you remember that the dot product, something like A dot B, tells us that, allows us to find the angle between those two vectors. So in this case, we're asked to find that angle, theta. And it's the angle between these two forces, F1 and F2. And first thing we're going to do is we're going to find the direction of F1 and the direction of F2. And we can do that by finding the directional vectors that we'll call R, that goes from A to B, and that has to do with F1, and the directional vector of that goes from point A to point C, and that's the same direction that F2 is pointing in. So to do that, we're going to need the coordinates of points A, B, and C. So we'll start by finding the A, or the X, Y, and Z of point A. And we see that point A is 2 meters in the X direction, 3 meters negative in the Y direction, and 3 meters in the positive Z direction. The next thing we're going to do is find the X, Y, and Z coordinates for the point B. And we see that point B is right on the y-axis, so that's nothing for X. It's 3 meters positive in the y direction, and it's flat on the ground, so it's 0 in the z direction. And finally, we want to do that for point C. You see that's negative 2, 3, and 4 meters. Okay, so we want to find the directional vector from point A to point B. So we go from B minus A, YB minus YA, and ZB minus ZA. Just plug in our values. Here we have 3 minus a negative 3, so that's going to be a positive. And then 0 minus 3. Again, don't forget to have units, in this case, meters. So we know that the directional vector from A to B is negative 2 in the x direction, 6 in the y direction, negative 3 in the z direction, meters. And then we're going to do the same thing for going from A to C. Again, C minus A, C minus A, and C minus A. Plug in our values that we determined already. Remember, units are meters. Plug that in, we have AC. Okay, now what we know is that theta is equal to the inverse cosine of RAB dot RAC. So the dot product of those two vectors divided by the product of their magnitude. Well, we need these values, and we need to compute the dot product as well. So the first thing we'll do is we'll compute the dot product. So the dot product of our two directional vectors, we take the products of each of the x components and the y components and the z components. Should be a C, Okay, so go ahead and plug those values in. -2, -4, 6, 6, -3, and 1. And we add that up, we get 41. So the dot product there is 41. Units would be meters. And then we also need the magnitudes. So our magnitude of that vector AB, square root 2 squared, x, y, and z. And that comes out to the square root of 49, or 7. And for the AC, put in the x, y, and z. We see that that is the square root of 53. Units is meters. Those will cancel out eventually anyway. So we can go ahead and back to our equation. Say that theta is equal to the inverse cosine of the dot product, which we found to be 41, divided by the product of the magnitudes there. So that's 7 and the square root of 53. And when we calculate that, we find that theta is equal to 36.4 degrees. So that's going to be the angle between those two forces, F1 and F2. Okay, in the third example and the last example that we're going to look at today, we see this bent pipe. So there's a bent pipe there and there's a force being applied to it. And the question is, what portion of that force is going along the AB, going along the pipe, going along that line AB? And we call that projection. So there's a force here, this force F, is going from the direction of point B towards the point C. And this pipe runs along the line AB. And the question is, what portion of the force is directed along that point, along the pipe AB? And so again, this is the second possible application we can use the dot product for. So to do that, again, we need to know the locations or the coordinates of the points A, B, and C. We start with A, B, and C. We want to know these coordinates. So we look at our diagram, and from the x, y, and z axes, we see that the x coordinate for point A is 0. It's located right along the y-axis. It's 1 foot positive in the y direction, and it has no z coordinate. You can get the coordinates for point B. It's in the negative z direction. And the coordinates for point C, which is right along the x-axis. So 2 feet positive, and again, no y, no z. So now we need to find our two directional vectors, RBA and RBC. The reason we want them is because we're asked to find what theta is. So we want to know what is that angle theta, and what is the component of the force F that goes along the line AB. So we can use theta in order to find that. But to get theta, we need to be able to do the dot product, and to be able to do the dot product, we need the two vectors. So we're going to find out these two directional vectors. So again, we're going from B to A, so the endpoint minus the starting point. And we're going to put that value in there. Okay, so we put those values into there. 0 minus 2 in the x direction, 1 minus 3 in the y direction, and 0 minus a negative 1, so plus 1 in the z direction. Our units are feet, and we see that the directional vector from B to A is going to go negative in the x direction, negative in the y direction, and positive in the z direction with units of feet. Okay, next we want to find going from B to C. So C minus B, C minus B, and C minus B. Look back at what we've already determined here for our coordinates, plug those values in. Okay, so now we have our two directional vectors. And we see that the line BC has no direction in the x. There's no I hat there. And that makes sense because we see that it doesn't move in the x direction. So it moves vertically up and it moves to the left in the y direction, but it doesn't move anywhere in the x direction, so that makes sense. Okay, so we know that we need to find the dot product. So we're going to take R BA dot R BC. We know that that's equal to the sum of the products for each one. So in the x, in the y, and the z. And so we plug those values in. When we do that, we find that the dot product is equal to 7 feet. And we also need to find the magnitudes of these. So the magnitude of BA is just equal to the square root of 2 squared, 2 squared, and 1 squared, right? 2, 2, and 1. And we see that that's equal to 3 feet, and the magnitude of the BC is equal to square root of 3 squared plus 1 squared, or the square root of 10. So now we can use the properties of the dot product to find that angle theta is equal to the inverse cosine of the dot product divided by the two magnitudes. So that's what I'm showing here is the dot product divided by magnitude. And when we put that into our calculator, we find that theta is equal to 45.2 degrees. So we have the first answer that we're looking for. Now the other question was, what is the projection of that force F onto the pipe, onto the line BA? Now, by definition, what we can do is we can take the dot product of that force F times the unit vector along the line BA. And that's going to be equal to, so we know that F is therefore equal to the magnitude of F times the unit vector that it's acting along, which is along BC, which would be equal to, we already found this along. So we have those values for F. For U, we know that that is equal to RBA over RBA. So we have all these values, and we could go ahead and plug all those in. But there's another way that's easy enough as well. So we could, again, take the dot product of these things, and there would be a lot of arithmetic, and we would arrive at the answer just the same. But we can remember that we've already found this angle theta. So we know that FBA is equal to F times the cosine of theta. Because by definition, we defined theta as the angle between F and the line BA from B to A. So we know that, in fact, we can just find it using f cosine theta. So I'm going to do it that way because it's easier. So f of BA is equal to f cosine theta, which is equal to, we're told that f has a magnitude of 80 pounds, and we just found that the angle is 42.5 degrees. And when we do that, we find that the answer is 59 pounds. Now again, you could go back up and use this definition, and you could plug in these values, and you would ultimately find the same answer. And you can go ahead and do that on your own. So that's it for these examples. Be sure to go through them carefully and be ready for the quiz at Class 6. We'll see you then.